Hello everyone, and we are going to share the screen. Here are the PowerPoint slides for a lecture on analog filters. So analog filters basically are filtering systems. They are not signals, they are system, but their job is to stop certain frequencies and allow other frequencies to move. So let's say if I look into a general category of low and high frequency going into a system, as you can see the blue and the red one, then the blue pass on because the blue is the low frequency and a high frequency signal will stop. Similarly, if you have a high pass system, then what will happen, the high pass filter, the both signals will go into, it will stop the low frequency signal, or we can say the low frequency component of the signal, and it will allow the high frequency component of the signal to go through. So the systems that we talk about, the filters, they actually work in stopping certain frequency components. So I can say filters um, works by allowing a certain frequency, by allowing certain frequency components to pass through while stop other frequency components. So as we know that from our Fourier series analysis and Fourier transform analysis, that the signals that comes basically consist of many frequencies. So once they pass through a particular system, then the system will stop them or will allow them to pass through. So filters can be used to effectively modify the signal. So there is a signal input and there is a signal output. So in this way, we can pretty much change the frequency composition of a signal. So I can say that um, uh, filters change the frequency composition of an input signal. So it changes, filters change the frequency composition. So let me emphasize more on this. So it's a frequency composition. It means certain frequency components are stopped where the other frequency components are allowed to pass through. So in this way, we can pretty much change the signal. Now, which of the components that we would like to stop, it depends on the noise component. So there are some frequencies that are present in the signal, and these frequencies are due to the noise. These are not actually the signal frequency. So we will stop the frequencies attached to the noise, whereas we will allow the frequencies which are important for the signal to pass through. In this way, we can clean up a signal. So keep in mind that filters basically works by allowing and stopping frequency components. So that's why one of the natural way of looking at the filter is that we design them in the frequency domain, whereas we apply them using convolution in the time domain. So we can keep in this way. Now, there are various types of these filters. So we can say that there are like active and passive wise filters. There are some filters which are active. There are some filters which are passive. There is one distinction between them, and I will go over this in this lecture. There are other filters which are called analog filters, and there are digital filters. So this is like a concept that we use in digital signal processing. In digital signal processing, okay, we take a signal and which is an analog in the beginning, and then we convert it to a digital signal, and then we design a digital filter and remove the noise, because digital filters are much more effective at removing the noise, okay, and then we bring them back to analog after cleaning. So this is one way of doing this. This is the topic that we cover in digital signal processing, DSP. Then another way to look at the filter is there are some filters which are linear filter and non-linear. I will say linear phase filters and non-linear phase filters. We will also discuss those later on. Then there are high pass filters, low pass filters, band pass filter, band stop, and all pass. Keep in mind the word band, okay, when we look at this word band means a frequency range, a frequency range. So it has nothing to do with the time. So band has nothing to do with, band has nothing to do with time. So keep in mind the word band is associated with the frequency range. It's a frequency range that it allows. That's why I call band pass, band stop. It means that it is stopping certain frequency range. It has nothing to do with the time. So the word band is associated and exclusively dedicated to the frequency domain. All pass, a very strange type of filter. I will like to say all pass is one of the very strange filter, because it does not stop frequencies. It allows all the frequencies to pass, but then it just plays with the phase part of it. So it does something to the phase. But this is something which we will touch in the advanced filter course. So here we are just going over a basic notion of what are filters. So our first and foremost important topic here is we will start with a very simple filters, which are passive analog filters. So when we use the word passive, that basically means that the filter is composed of components that does not generate any energy. So it means all the energy that is coming to that filter is basically coming from the input side. So the system itself does not have a power source. So that's why it is called passive. And all the energy that comes from the input side, okay, that basically when we pass through the filters will have some loss of energy. So it's like here is a filter, okay. So the energy is coming from here, energy input. And from here we take energy output. So definitely the energy output is always less than energy input, okay, because there will be some loss at the filter, because the filter is passive filter. But there are some active filters like operational amplifiers. They have their own power supply. Because of that, it may be possible that you get a signal which is at the output, and that signal has more energy than the input, just because you are feeding. In case of active filters, so if it is a filter and that is active, then it means that you are feeding power to it. You are feeding power to it. So in that way, um, the power or the energy that comes out at the output may be more than the energy that was plugged in by the input, okay. So that is an input, that is an output. So active filters can generate outputs with larger power than the input, whereas in case of passive filters, the output energy is always less than the input. So for the time being, let's concentrate more on those passive filters. So I will say, okay, so I will just, so let's look into this passive analog filter. So no power source, and we are trying to do the filtering. Okay. So for that situation, as I told you that the filters has everything. Whenever they are doing filtering operation, they always do the filtering operation over the frequency. So our first design step, when we are trying to design a filter, we actually start with its specification, what type of filter we want. Always we start the specification in the frequency domain. So the filter specifications are defined. I will say, um, so, sorry, the filter specifications. So the filter design specification are provided in the time domain. So it's mostly what you're looking into is that the specifications are defined. So here is one such specification given for a low pass filter. So low pass, as the name suggests, that it is a filter which will pass the low frequencies and it will stop the high frequency. So we have what is called as a corner frequency, which is the barrier. Before that barrier in frequency, we have a constant amplitude. We are allowing all the frequencies to pass. As soon as the corner frequency comes, then we give zero amplitude. So this is what we want. We want that all the frequencies that are less than FC, we should get an amplitude of 1. So all the frequencies which are greater than FC, the corner frequency, we should get 0. So it means we are completely stopping the frequencies greater than FC, which is a corner frequency, and all the frequencies which are less than FC are allowed. So FC is a kind of cutoff frequency, I can say. We can also call this as cutoff frequency. So it means this is kind of like barrier in the frequency. So before this, we want the frequencies to pass, and after this. So this assume that this is a specification and this is given in the frequency domain. So now we have to figure out um, the filters which can adopt this behavior. But keep in mind, this is an ideal behavior. So filters will never adopt the ideal behavior, but they will come closer to this behavior. So here is so there are some other terminologies that we use when we talk about filters. So if we have a low pass filter, then the region that is allowed to pass is called pass band region. Whereas the other region, which is does not allow to be passed, rather stopped, then it is called stop band region. Okay. In case of high pass filter, in the beginning, we don't allow the frequencies to pass. So stop band comes in the beginning and the pass band comes after this corner frequency. So after FC, we have this pass band. Okay. And in case of these band pass and band stop filters, you can see very clearly that it has two corner frequencies, FC1 and FC2. So between these two from starting frequencies, starting from FC1 to FC2, we allow the frequencies to pass. And in case of band stop, between FC1 and FC2, we stop the frequencies to pass. So any frequencies before FC1 and frequencies after FC2, we allow them to pass. So it's a band stop filter. Mostly it is used, like for example, in medical signals, ECG signals. You mostly have this 60 hertz line frequency that is coming. So in order to remove the 60 hertz, we make a band stop filter that is concentrated around this 60 hertz. So we want the 60 hertz signal to be stopped because this is the noise. This does not belong to the signal that we are looking at, the ECG signal that we are looking at. So this is the first step we do in cleaning the ECG signal. So we have band stop, but keep in mind the axis. You see all the specifications are given in the frequency domain. You see, there is no time reference here. So whenever we start on designing a filter, we always start designing the filter from the frequency domain. So these are the ideal characteristics that are given to us in the frequency domain, and now we have to design a filter based on those specifications. Okay. So let me take you back to one of those electrical circuit concept, which is uh, a simple voltage divider. So we are starting now to design the filters for this. We will take advantage of this voltage divider circuit. As we all are aware of, the voltage divider circuit is that there is an input voltage, okay, plus minus input voltage. And then because of this input voltage, the current will start flowing in this part of the circuit. It will go through R1. And then the same current that goes through R1, that same current will go to R2 because this one, the other end, which is going outside, is open, and an open path cannot have a current. So current cannot divert. So the same current that goes through R1, the same current that goes through R2. So if I basically equate and apply the KVL, then if I simplify the Kirchhoff voltage law, I will end up with this equation. So V out is equal to, you see, V out is across R2. So V out over V in is equal to the resistance R2 divided by the total resistance R1 plus R. So this is our voltage divider relationship, and a very important one. But keep in mind, in this particular relationship, there is no mention of frequencies, no omega. So once we have no omega, so it means it is a voltage divider that will give us, that will divide the input voltage, okay, that will divide the input voltage regardless of the frequency. So this voltage divider divides input voltage, divide input voltage without frequency, without omega. So it works, and it does this division without taking care of the frequency because there is no frequency variable in this relationship. Yeah. So if you check out the relationship, there is no frequency, no mention of the frequency. Okay. Now let's do a small variation and go to another one. Here, you see we have, instead of R1, R2, if you remember, our circuit was that there was a V in plus minus, and there was this R1, and then we have R2, and across R2 we were taking the voltage V2. So to keep that we can say this is the voltage V out. So we were taking the V out across the voltage across R2. Now here we keep R1 as the resistance, okay? But for the R2 part, you see this R2 part, which was the resistance, now we replace it with a capacitor. Now, capacitor is a frequency dependent device in the sense that its impedance, we don't say resistance because it has a magnitude and a phase part. So the impedance of a capacitor changes with frequency. So capacitor is a component that will provide resistance to the current that is flowing based on the frequency that is present in that particular current. So it is a frequency, it is a frequency dependent device in the sense that it changes its behavior based on the frequency. For example, let's say we look at two extremes. In one extreme, if you check out and say at frequency 0, so if the input signal that is coming, in case of this voltage divider, it's a current that is coming. So if that current that enters, so the current is flowing in this way. So this is a current. Now this current become now a part of omega. So and in this omega, frequency is 0 because omega is 2 pi f. So now this whole thing becomes 0 because f is 0. So omega is 0. So if that frequency comes, then we know that the impedance of the capacitor is given by minus j over 2 pi fc. Now f is 0, so it means the denominator goes to 0. So in the limit, the zc will approach infinity. And infinity means if a circuit element has impedance that goes to infinity, that means that the path become open. You see that the path become broken, it become an open circuit. So an open circuit behavior. So now if you check at the V out, when something is open, it means the current will not flow from the input voltage through this one. So all the V out will become equal to V in because there is no loss in this resistance as there is no current that can flow because the resistance and capacitor were in series and now the capacitor become an open circuit. So of course there is no current flowing in the resistance R. So there is no loss and all the voltage V out will be equal to V in. Okay. Now let's look into the behavior at when RC filter at F equal to infinity. So when F become infinity, very high frequency, what happened? The impedance of the capacitor, as I told you, it's a frequency dependent. So the denominator get infinity. So it means that 1 over infinity is almost approaches 0. So ZC becomes 0 and it becomes short circuit. You see, it's grounded. But when it's short circuit, all the V in will come across this R and 0 voltage will be at the V out. So you see, before our V out was equal to V in, and now our V out is equal to 0. And this change in our voltage is dependent on frequency. We haven't changed the amplitude or the voltage supply here. We only change the frequency of our voltage supply, and we are getting a completely different voltage at the output. So this is basically the moment you make an RC architecture instead of a common voltage divider, you will figure out that it becomes a frequency dependent circuit. So our circuit is frequency dependent. So it's a frequency dependent circuit, or I can say frequency dependent voltage divider. So the same voltage divider, but because of the introduction of the capacitor, it becomes a frequency dependent. It depends on the frequency. It changes with the frequency. You see, when we have F is 0, we get same as the input. And when F was infinity, very high frequency, we got 0. So based on this behavior, now look at this one. And now you can imagine I interchange the location of the R and the capacitor, the resistance and the capacitor. And now this, we can figure out yourself that this will behave like a, you see in the previous one, it was a low pass filter. Now this configuration will give you a high pass filter because you can check later on yourself what happens when F goes to 0 to the V out. Okay, and when F goes to infinity, so when F goes to infinity, then what happens to V out? Based on this, you can figure out that this will be more or less like a high pass filter. So when we say high pass filter, it means that it will pass high frequencies and it will stop low frequencies. Okay. Now, if we go back to our RC low pass filter, okay, so our RC low pass filter, our ZC, which is the impedance at the capacitor, is equal to minus J over omega C. Okay. And now our V out will be equal to, according to the voltage divider rule, so V out will be equal to ZC, the impedance across the capacitor, divided by the total impedance, which is R plus ZC. So if we play and plug in the values, okay, and we did a little bit of cleanup, then you will figure out that omega C is in the denominator and omega C is in the numerator, so they can cancel out. And we can pretty much do this thing minus J over this omega C R minus J. Okay. So pretty much omega C is cancelled with omega C, and now you have a different kind of behavior. So your V out over V in does not even contain magnitude. It will also contain some phase part because of the presence of this complex number J, because J is minus 1 under the root. It's a complex number. Okay, we'll come back to this later on. So let's move forward and look into the behavior of the phase. So you can see that the current that is flowing in this circuit, it will pass through the resistance R, and at the same time, it will pass through the capacitor. Now, when it passes through the resistance, then the voltage across the resistance, which we call VR, and the current that is passing through the resistance, they are in phase. There is no difference. But when the current passes through the capacitor, and if we measure the voltage across the capacitor, we will see a 90-degree phase shift between I and VC. So there is this I is the current that passes through the capacitor, and VC is the voltage across the capacitor. So there is a 90-degree phase shift between I and VC. However, the current that passes through the resistance and the voltage across the resistance, they are in phase. Okay. Now, if we look into specifications that are given most of the time when we design a filter, we mostly basically provide the specification in a dB and log plot. So you see the frequencies are given as a logarithmic plot. For the frequency axis, this is a logarithmic plot, 1 hertz, 10 hertz, then 100 hertz. So this is log 10 of f, okay? Whereas the vertical axis that you see is given for the magnitude, and it is given as given 20 log of V out over V in magnitude, okay? So this gives you a dB plot. So the dB plot is given for the vertical axis, and on the horizontal axis, a logarithmic plot is given. One thing you can see very clearly that till 10 hertz, we are getting 0 dB. It means we are allowing it without any changes to the signal. And as soon as the signal components, frequency components, move beyond 10 hertz, it comes down. So it becomes, the dB become negative because below 0. So negative dBs are called attenuation. So you are getting attenuation for different frequencies that are beyond 10 hertz. So 10 hertz is a corner frequency. Mostly when we define a corner frequency, we can see very clearly that the corner frequencies basically are defined at minus 3 dB point. I will tell you what I mean by minus 3 dB, but for the time being, assume that there is a point where it goes down below 0 dB to minus 3 dB. And exactly at that point, at this minus 3 dB, because this point is minus 3 dB. At minus 3 dB, whatever the frequency we get, we designate this frequency as corner frequency. So anything below this, definitely the dB goes negative and attenuated, and after some time it's completely attenuated, but there is a slope. Whereas in case of ideal low pass filter, we want an abrupt change. What we want is that before FC, look at the red line. The red line is the ideal line. So in case of this ideal behavior, we want everything before FC to remain at 0 dB. It means no change, neither amplification nor attenuation. But as soon as we pass FC, there should be, it has an abrupt change. You see this red one, it comes directly 0, and after this it becomes 0. Whereas in case of a first order RC filter that we design, we will find out that there is a slope. It gradually decreases, increases the attenuation. So it's a gradual, I can say, it's a gradual increase in attenuation. So it's a gradual increase in attenuation. It's a sloppy behavior, slope. It goes down, 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 down. So it has this slope. So it goes down. So this is an actual IC RC filter. So it's a first order RC filter. That's whereas the red one, the characteristic that we see with a abrupt change. Okay, so here is comes and abruptly it goes down. This is ideal low pass filter. Okay. Now, as I told you, the FC, we usually go for minus 3 dB point, okay, because of this minus 3 dB point. Now, keep in mind when we have an ideal filter, the specification are only defined in terms of the magnitude part. There is nothing to do with the phase part. Whereas in the reality, when we do design a filter, the filter will have some magnitude plot, and at the same time, it will have a phase plot. So in other words, it will not only, when we design, it will not only change the magnitude according to our specification, so it has a slope, but it will also change the phase of the frequency component. So our biggest wish is when we are designing an analog filter that we want the phase to be linear phase, and I will tell you why I want. So in magnitude, we want it to behave like nothing, and after this we have this slope, and then we reduce the attenuation. But in case of phase plot, we would desire to have a linear phase because we cannot have zero phase as the frequency specification for the ideal. It has a zero phase part, but we cannot have. So we will desire to have at least linear phase. We will not go for non-linear phase. So any filter with a non-linear phase is not acceptable. Okay. Now, if we look into our course, which is signal and system, which is about Fourier series and Fourier transform, so we can think of our filter as an LTI system. So our filter is an LTI system. So every LTI system, so I will say every LTI system is represented by, okay, by something which we call impulse response. Okay, so system is represented by impulse response. And what happened is since we are dealing with the frequency domain, the Fourier transform of the impulse response is of frequency response. So it is frequency response. So what we have is more and less, if you look into it, it is h of t, which is the impulse response. And after Fourier transform, this become h of omega. Okay, so h of omega is the frequency response of a system, and h of t is the impulse response of the system. So it means h omega and the small h of t, they basically representing the same system. One is representing the system in time domain, and the other one is representing the same system. In our case, this system is a filter in the frequency domain. So what happens for an LTI system? Okay, so here is our filter. And now here comes the signal x of t. And the filter has h of t, impulse response. So when the output comes out, this is y of t is x of t convolved with h of t, not multiplied, convolved. So this is convolution. But this is only true for LTI system. Now, when we look at it in the frequency domain, this x of t become x of omega, and h of t become it becomes I will say so it become h of omega, and now our y of t will become y of omega. So this becomes x of omega multiplied with h of omega. So convolution become multiplication in the frequency domain. So the whole behavior of the filter is it takes the Fourier transform of the input, multiplied it with the frequency response of the filter, and give you the output. Now, this gives you a very good explanation of how the filter works. So if you decompose your input signal into an exponential Fourier series or in Fourier transform, you will see that you will get some exponential component. You will get e to the power j omega 1. You will get e to the power j omega 2. So there are a couple of frequencies. Now you have h of omega. So maybe h of omega 2 is 0 and h of omega 1 is 1. So it will allow this e to the power j omega 1 to pass, and e to the power j omega t, this is completely cancels. So this is how the filter works. So when we multiplied the frequency response tells us how it will behave with each independent frequency component. So h of omega will treat each frequency separately based on what type of frequency is coming. So maybe for some frequencies, it has a very high amplitude. For other frequencies, it has a low amplitude. So that is how the filtering happens. But keep in mind, it is just a multiplication. So it is a frequency-wise multiplication. So omega 1 frequency of x will multiplied with the frequency response at omega 1. Then omega 2 of the input signal, which is x, will multiply with omega 2 of the frequency response. So it's a frequency-wise multiplication, and it clearly gives you an idea of that, that a result of this multiplication will be some frequencies will be stopped and other frequencies will be completely attenuated. Okay. So now let us move towards the next part, okay, which is our LTI behavior. Now you can see very clearly here that the filters can be represented in a signal system by an LTI system. So we say filters are represented by LTI system for simplicity. That is how we study them Okay, so we simplify them. So our first simplification, or we can say the first approximation of any filter, is that we represent him as an LTI. So forget about this omega thing, because this is digital filter. Okay, we only talk about analog filter. So this is the analog side, and the lower one is the digital side. So we'll talk about later once we go through the sampling process. Okay. And now I would like to share with you some of the responses that we got. The impulse response of a continuous time ideal low pass filter is the inverse continuous Fourier transform of its frequency response. What happened is that if you give a response, okay, in omega, so let's say this is omega, now you have to go from minus pi by t to plus pi by t, and there the capital T is the response here. Now if you have this kind of ideal low pass filter in your frequency domain, in which you have a sharp edges, you will find out that if you take because this is your impulse response, okay, in frequency domain. So this is frequency response of an ideal low pass filter. We want impulse response. So in order to go from frequency response to impulse response, we will do what is known as inverse Fourier transform. So if I apply this inverse Fourier transform, then you will find out that our frequency response becomes a sinc function when we go to time domain. So you will find out that it's an infinite, this is h of t, and this one is h of omega. So here is h of omega, and here is our impulse response. So an ideal low pass filter, actually, when we take it to the time domain, we see that its impulse response is a sinc function. Now, there are many problems with the sinc function, because sinc functions cannot be realized in real time because it has an infinite support. It goes from minus infinity in time to plus infinity in time. As I told you that the Fourier transform are designed in frequency, but they are applied in time. So when we come to application, we cannot apply them because it becomes a large sinc function. So many other changes we can make. One is the window function, window method of designing filter, in which we truncate, cut our impulse response h of t from both sides. Okay. Here I described again this impulse response and its behavior in time. So the frequency domain behavior is it goes from minus omega c to plus omega c, and here is 1. This is the equation. I'm just plotting the graph of this equation, and it is 0 before that. So if you just do 0 before that, and suddenly it becomes 1 between this minus omega c to plus omega c, and then 0. Now this omega, when transformed to the time domain, you see this is the time domain picture. So here is this time domain picture. There is no omega here. Omega c is not omega, it is a constant. Okay, so here is time. So if I convert it to time axis, we will see that it is a sinc function. It goes at the peak and then comes down and then ripples through, and every time its magnitude is decreasing. Similarly on the left hand side. So this particular impulse response is a non-causal. It has this negative part. So because of that, it becomes a non-causal. And now there are certain implications of a filter to be non-causal, because if a filter is non-causal, it means that the output at a given time will depend on the future input, which is not possible in real time. That is why these ideal low pass filter cannot be implemented in real life. okay, because they have these non-causal behavior, okay. So here I give you a definition of a causal filter. So very important that once you are designing that, do you want to design a causal filter or anti-causal filter? So if you have a causal filter, then you have to be careful with the HT. So HT should be 0 for t less than 0. Whereas in our case, this is not the case because we are getting a sinc function on both sides. That's why that sinc function tells us that the filter is not causal. So we cannot implement it in real life, in real time, because the input will depend on some future. So output at a time, let's say t naught, will depend on inputs which are at t naught plus 2t naught, let's say. So it's like this is a future. This is a future input. So our output depends on the future inputs. That's not possible. How come if I'm doing a real-time processing, I don't know the future inputs, what the inputs will come in the future. The signal is coming as a sequence. I can only depend on the past inputs, yes, but I cannot depend my output on the future input. So this makes the filter non-causal. So the ideal filter that I shown you is not realizable in real time because it's a non-causal filter. Okay. There are other things that you cannot do because you have a sharp cutoff. You remember that in ideal filters, we have those sharp cutoff when it goes to the frequency, those sharp cutoff. You see this sharp cutoff? So we cannot realize this sharp cutoff in omega. We can gradually taper in, but to realize this one, we need an infinite amount of memory when we are trying to do a hardware design of the filter. So these sharp transitions are not realizable. Now here is an example of the car suspension system. This car suspension system is also a low pass filter because what happens whenever a jump comes, the suspension will absorb the high frequencies and will allow the low frequencies. So it means it will slowly move the body of the car, but it will not give you up and down high frequency jumps. So all the high frequency jumps are being absorbed. Only the low frequencies are allowed to pass to the body of the car. So that means that the car suspension system is actually a low pass filter implementation, but it's a mechanical filter, okay? So now let's move into that we don't like this behavior of our filter that it tapers the attenuation. So the attenuation does not abruptly change, but it tapers in. But we want to reduce the slope of this attenuation that happens in the stop band. So in order to increase this attenuation, slope of attenuation, you see this? In order to increase the slope of attenuation, we implement higher order filters. Now, when we say higher order filters, we basically means that we are adding more stages of this RC filter. So we have a second stage, we have a third stage. So we have a first stage, second stage, third stage. So these are all the stages that we add in order to improve. So with every stage, we are getting a better slope. You see this? First, the slope was this, then another slope, another slope. So you see, we are getting better and better by adding the stages. We are getting closer to that abrupt change that we want in our low pass filter. We are reaching to that abrupt change. Okay, so every time we add a new stage, we are getting like minus 20 dB per decade to minus 40 dB per decade, then minus 60 dB per decade. So that is how we are really increasing. So minus 60 dB per decade is a much better filter because it is more closer to the ideal behavior. but we pay a price for it because we have more stages. Now, when you have more stages, you have to be careful, because every stage that we add, it provides a loading effect. In electronics, we come across something which is called loading effect. So the second stage become a load on the first stage. So we have to be careful for what is the Z output impedance and the input impedance of the next stage. There is a relationship we need to maintain in order to avoid loading. Otherwise, it will draw a lot of current, and then the voltage at the output will drop. So as a rule of thumb, mostly when we have these cascade design, so we look into that the Z in should be at least 10 times the Z out. Okay, so this is our what you call them, the rule of thumb for the design. If we follow this rule, then there is a chance that we will not be having what you call them, the loading effect. So we can have many stages, but then we will avoid the loading altogether. Okay. Um, so you can see, so what is our Z in? So in order to calculate Z in, we will use our assumption of F equal to infinity. So it's a worst case scenario. So for F infinity, the Z in came out to be R, because this will become a short circuit. Okay, and we are looking from this side. So this is our input impedance. And at F equal to 0, I will calculate the output. So I will look from the output port into it. So then the Z out, this become open circuit, and again I see. So it means in both cases, Z in and Z out, both are equal to R. So it means they both depends on the R. So in other words, my design should be, if I want to have a second stage, then I need to make the second R 10 times R. You see? So this is a 10 times R I have to put in here. Then the next stage should have 100 times R, such that we avoid the loading effect. But now the problem is that our resistance is changed, and this will change the corner frequency. So in order to avoid the corner frequency, I have to bring the capacitor here also lower than 10 times. And here this capacitor should be 100 times lower. So once I reduce the capacitors to this small value, they become picofarad, and they become so sensitive that I cannot have those capacitors when I'm designing it. So it means it become really not a elegant solution. So we have to find an elegant solution. We wanted to decrease the slope of attenuation. Okay, we wanted to decrease, this is our goal, decrease the slope of attenuation. Okay, but we don't want it to play with the capacitor, a small capacitor. Okay, so for that we will adopt some other methods that I will describe in the next class. So I will stop my class right now. So if you have any question, you can send it to me on the YouTube, and you can also post it in the WhatsApp group. Okay, so thank you very much, and I will see you next time. Okay, so I will stop my share, and I will stop the